Yes, hi, I'm Lexin Ding, and my talk will be a direct follow-up on our last talk about IDMFT. And this is joint work by Julia and Christian and I on some assessment on this new IDMFT method. So a bit about myself. I'm not super well versed in DFT or RDMFT because I don't work in this subfield. I usually work with fermionic correlation entanglement and its applications in main electron systems. So you can actually imagine my excitement to learn about Collins conjecture and this method, and to see that in some cases it works so well. It actually shows a lot of promise. And I think it's important to really understand the up and down side of this method and start a conversation, because this direction actually looks really promising. So let me quickly start. Yeah, so just to recap a little bit of the method described in the last talk. So IDMFT is first and foremost should be a 1-RDM functional theory designed for a Hamiltonian of this form with a fixed two-particle interaction. And what we want for this problem at the end of the day is a universal functional that can take the 1-RDM as an argument and give us the correct energy. And I apologize for the abuse of mathematical language. I should use square bracket for functional. Okay, and the premise of this entire method is based on this so-called Collins conjecture, or the modified version of it. So the cumulative energy defined as the Hartree-Fock function, difference between Hartree-Fock functional and the exact functional. The conjecture states that you can approximate this cumulative energy by a linear function of the entropy of your 1-RDM, or the entropy of the natural occupation numbers. And this entropy is designed for fermions. So it's a particle hole symmetrized entropy. So you see there's one term that involves the one particle RDM, and the second term actually involves the one whole RDM. So this is already a departure from the original Collins conjecture. But this quantity itself actually has a really rich quantum information meaning. If you measure the distance between your state and states that are so-called quasi-free, namely states that can be completely characterized by 1-RDMs, and you measure the distance using relative entropy, and you ask how close this system can be, then you can actually prove that this closest distance is exactly this particle hole symmetrized entropy. So in some sense, in a quantum information perspective, this quantity is exactly the correlation among identical fermions. And on the other hand, the cumulative energy is the intrinsic correlation energy defined in a chemical sense that, for the system. So it's very exciting to see the direct connection here between these two perspectives. And that's why I think there's deep reason why this method works for such systems, and we should definitely think very carefully about it. And as we saw in the last talk, this 1-RDM gamma, which is a tuple of the natural occupation numbers and the natural orbitals, is obtained self-consistently, because you have a modified Fockian, you can do it in a self-consistent way, but you have to decide first how to assign these kappa and b in this conjecture, and they are prefit by some input data. For example, you have two geometric solution using Fuzi method. You can use this to determine kappa and b, as Zhang mentioned in the last talk. And from then on, you can get the cumulative energy for the entire spectrum of different geometry. So that's the whole main idea of this method. And it can actually perform quite well. For example, for hydrogen, H2, first, you can get really accurate ground state energy for all different kind of geometry, so different separation distance. And also, very impressively, you can recover the correct mixedness in the dissociation limit. Namely, you can actually get the correct occupation number in dissociation limit using IDMFT. So this is actually rather amazing to see. So we saw how well it performed, but what can go wrong is the rest of the talk. Okay, first, let's think about the premise. The premise is the Collins conjecture. The premise is in this red box. If this equation holds, then it's more likely that your method will work. Okay, does this equation hold? Yes and no. For example, if you fix electron number Ne, and also you fix the nuclear charge for systems like H2 or helium-22 plus, so I increase the nuclear charge, but I keep the number of electrons the same, the linear relation is really, really, really good. And as per our discussion about 10 minutes ago, we still don't understand why this works, right? So there are theories. We still don't know why this works. And the most important thing is there's this entropic quantity here with the logarithm, and that's really, really tricky. Okay, then here you already see, okay, works, but not fully. Namely, you have to use different kappa and B to establish this linear relation, even for the same number of electron, but different nuclear charge. So here, if I change the nuclear charge, then the slope of this linear function would change. Then it means you need a different kappa and B for different molecule that you consider. Then this is no longer universal functional. You're giving up universality entirely. And additional issue arises, as Yesi was pointing out, that when you do differentiation, then you leave the energy hypersurface. So this is really a functional that is defined for each molecule separately. Okay. And still, these look very, very linear, but exactly, they're not exactly linear. So you do have to somehow statistically fit kappa and B, and you do need some input data for this. So this is another downside. And perhaps the biggest downside is that this equation in the red box, this Collins conjecture is not always correct, in a sense that the cumulative energy is not always a function of S. For example, the system that we look at is a rather peculiar system. So it's a helium hydrogen plus. In this case, you still have 2 electrons, but you have a asymmetric dissociation. So we vary the distance between the 2 atoms, and we see that this is no longer a linear function. It's not even a function. So in situation like this, how do you decide kappa and B, and would your program still be stable, and would you even converge to any solution? That's, yeah, there's that. Okay. So we know that the Collins conjecture is not always correct, but let's assume that it is correct for certain system, which is true. And let's say that we can confidently fit kappa and B. The next question is, okay, we can, in H2, for example, recover really accurately the ground state energy, but what about its components? So there are 3 different sources of energy error. So I split into kinetic energy error, potential energy error, and the 2 electron energy error. And the first 2 are 1 particle quantities. So if you want to really test whether you get the correct 1 RDM, you really need to look at these quantities. And you can see that as you dissociate, these errors actually goes quite big. For the 2 particle error, it's maybe slightly above the chemical accuracy. So it's more than a few millihartries. But bear in mind that when these 3 terms all add up, they are within chemical accuracy. So you can see that in dissociation limit, you are facing hundreds of millihartry in the kinetic energy error and the potential energy error, but somehow they magically try to cancel each other. And at the end, your total energy is not that wrong. But these, how do I go back? These gap here, it clearly shows that you don't have the correct 1 RDM, because if you have the correct 1 RDM, you wouldn't have this such huge gap. And this is precisely what we check. So in this plot here, we plot the distance. This is a distance function I will explain later, between the gamma I, the 1 RDM obtained from IMFT, and the exact gamma from full CI solution. So you can see that at the beginning, the error is okay. Maybe it's within chemical accuracy, but when you go further to dissociation, this is not negligible error in your 1-RDM. And this distance function that we define here is the Frobenius norm. So it's defined as the square root of the trace of this quantity here. And by studying these distance functions, instead of looking at observables alone, you get a more universal picture, namely the expectation value of any observable, the difference between expectation values of the observables between two density matrices is bounded from above by this distance between the two density matrices. So if your two states are close to each other, then you can put a really good bound on the accuracy of your one particle observables. But if not, then there is no guarantee. It means that you get bad natural orbitals, you usually tend to have bad one particle quantities. And this is not what we want from a good RDMFT theory. And let's now have a little Gedanken experiment to see why can't it in principle get a good 1-RDM. Let's consider the hydrogen, our favorite molecule in dissociation. So each atom would capture one electron, and the ground state, you can equally likely to find these electrons to be either on the left or right or spin up or spin down. So you can easily write down the correct 1-RDM as an equal mixture between all these left, right, spin up, spin down states. Okay, and we have this exact solution. And what happened when we plug this into the Hartree-Fock functional? So the Hartree-Fock 2-RDM is simply the tensor product between gamma and gamma, but you apply this exchange operation. And as you plug into the Hartree-Fock functional, you obtain terms that represent interaction effects between nucleus, and you get additional term that represent interaction within each nucleus. And this is in direct contradiction with the situation that your molecule is dissociated and each atom only has one electron there. And this discrepancy is a two-particle effect, and it's unlikely to be canceled by one particle quantity, such as the entropy of the natural occupation numbers. And after we put these results on arXiv, the author actually write a very nice reply. And they also show that if you compare the orbital obtained by IDNFT to the full CI solution, of course, they look different. And they actually look quite so different that it leads to the error in the one particle energy that we saw before. So as I said that these kind of on-site interaction terms is unlikely to be accommodated by one particle quantities. And that's why in this reply to our reply, they suggested an additional modification to the original Collins conjecture, namely they multiply the entropy with an exchange term like this. And by this, they not only still keep the nice property that they can converge to really good occupation numbers, but now they also converge to the correct orbital energy. But whether or not the 1-RDM is still different than the exact solution, that is yet to be seen. But if you change the Collins conjecture like so, and you can still recover good energy and good occupation numbers, isn't this in direct contradiction with the original Collins conjecture? And we checked that actually for H2, this is actually very, very accurate, that we see that it's almost perfectly linear. Then what is the story here? What is the motivation now for this functional, and why is it different than a Collins conjecture, which is already validated in this system? So this really show us that applying quantum info quantities and using them directly to modify your functional this is very, very deep water, and one should really, really be cautious about it. So it's not that we are trying to very hard to criticize this work. We like this work very much. It's a direct connection between quantum info and RDMFT. And I think it's very, very exciting. But it opens up so many questions that I think the two communities should really think about it together. First is that we know that the Collins conjecture is not always correct. And the natural question is, when is it correct and why it works when it works? And this is a very deep question. Otherwise, it would have been proven a few decades ago. And the second question is, now that you know that the Collins conjecture is not always correct, then is the convergence of IDMFT even guaranteed? So do you have theoretical foundations such as Hartree-Fock theory that safely guard your method? And practically, you still need to pre-decide these two coefficients to fit a Collins conjecture. And how do you choose these numbers? And there are many ways to do so. In the original paper, they choose kind of a 2-point method. So you only need 2 points to fit a line. In the reply, sometimes they switch to linear regression. And how does these different methods affect the accuracy of your ground state energy? This is also not conclusive yet. And maybe this question is more interesting to me and our group, is the fundamental entropy the only relevant or useful quantum info quantity that we can think about? Can we use Renyi entropy, or does it mean that we just need to pick a really well-designed Schur convex function? And actually, we do a little demonstration here. Is that, okay, we designed this A function that looks very much like the particle hole symmetrized fundamental entropy, but we put these additional how do you call them? Exponents in the natural occupation number. And we try to, well, this is a very well-chosen exponents. So we compare to the IDMFT results. So this y plus A is the Hartree-Fock functional plus this term designed by us. And you can see that it gets actually much better than IDMFT. Yeah, so it opens up a whole branch of questions how to design new functionals based on 24 quantities. Yeah, and as I mentioned in one of the previous slides, the discrepancy that is caused by the fictitious on-nucleus interaction, this is unlikely to be canceled by one-particle quantities. Doesn't mean that we need to start looking for quantum information quantities that is defined on 2 RDMs instead of 1 RDMs. So this is even bigger questions that cannot be directly answered right away. And in this slide, I just want to start the conversation because there are many RDMFT experts in the audience. Is that what do we actually look for in a good RDMFT theory? So this is independent of whether or not we choose the quantum information motivated approach. So first of all, we want the theory to be able to recover the correct static correlation in association limit. So the mixedness in your 1 RDM should be reflected. And we want that your functional to be having the correct scaling in the boundary of your domain. This is the so-called exchange force, which Julia and Christian has some work on this. And also just in our audience, he knows very well about the size and volumes extensitivity and these kind of criteria that is demanded on the functional. And of course, we want not only accurate ground state energy, but we also want different one particle quantities to be also accurate, such as dipole moments and kinetic energy. And this is something that we should bear in mind, not be blinded by the accuracy of the ground state energy alone. Yeah, so right now I would welcome questions, and also if you have any comments, feel free to join in.